Hey everyone, welcome back to the Physics 30 Unit 2 videos. We are doing a continuation of our centripetal force continued lesson. This is video number 3. So we had just finished talking about an additional requirement when we're talking about vertical systems and circular motion. And so in the previous example we had looked at what happens when we have, say, centripetal force and we were working with a bucket tied to a rope. So an object moving in a vertical circle is affected by the following forces. So the centripetal force is the net force on the object in any position. The centripetal force is determined by the object's mass, speed, and radius. The force of gravity is one of the forces that may contribute to the centripetal force, but as we saw in the last video, it might not necessarily affect it depending on if the object is completely to the left or completely to the right. And the force of gravity remains constant regardless of the position of the object. That is, provided we are on Earth, of course, which, I mean, we're not going to be looking at other examples, so that's fine. Okay, so how does radius affect speed? So let's look at a specific case of one of the factors that affects speed. So suppose a disk is spinning about its axis with uniform circular motion. So looking at our picture, we have 3 different positions that we're really considering. We have positions A, B, and C here. And so as you notice here, one has a smaller circle, and then we get a bigger circle and an even bigger circle as well. So they're all at different radii from the axis of rotation, with A having the smallest radius and C having the largest. We know that points A, B, and C will complete one revolution or one cycle at the same time, so they will have the same period. So when comparing the speeds though, point A has the smallest radius, so it will actually have a slower speed in order to make sure that this period stays the same. It has less distance to travel around that circle, so it's going to travel slower. So that also means that point C is going to have the fastest speed because it has more distance to travel in the same amount of time. Let's actually spell this correctly here. There we are. So from this we can say that the radius is directly related to an object's speed. Alright, so now we're actually going to go back and look at our centripetal acceleration equation and our centripetal force equation. And what we can do is we can substitute in our equation for centripetal speed or the circular speed, plug it into those equations, and then we are going to end up with some simplified equations that don't involve speed. So this can be very handy if, say in the question, we weren't given speed. So this will help us save a step. So we'll start with our first acceleration equation. So as I said, we're going to take this equation here and substitute it in for speed into our acceleration equation. So your centripetal acceleration is equal to, so it'll be 2 pi r divided by your period, and that all is squared, divided by your radius. And that here, remember, I'm substituting it into this equation right here. So we can simplify this equation just so it's a little bit easier to work with in questions. So we can apply the square, and we're going to apply to each term or each value in the fraction or within the brackets there. So 2 squared is 4, and then pi squared, we're just going to leave it as pi squared so that way we don't have to worry about rounding issues. Then we have our radius squared, and that's all divided by our period squared. The last little part here we have to make sure we don't forget is that all of that is being divided by your radius. So this is looking pretty gross. I'm probably reading your minds. Maybe you're thinking this looks horrifying, and I mean, I agree with you. It's not a nice looking equation. So, but what we can do though is we can simplify it. So what we can do is we can rewrite this part of the fraction, this divide by r, as a fraction and multiply it. So we can just rewrite it so it looks different, and it'll help us to simplify. So your centripetal acceleration is equal to, so that's 4 pi squared r squared divided by your period squared, and then multiply, you want to write this as a fraction. So this will be 1 over your radius. So from here, what we can notice is that we have a radius on the bottom, a radius on the top, or I guess in fact we have two of them since it's being squared. But so we can cancel out one of the radius on the top and the radius on the bottom. So then we have a much more simplified equation. So we have 4 pi squared r divided by your period squared. All right, so now for our second equation. So here we're going to be looking at force. So we could actually work with this equation right here, but if you want to save yourselves a step, we actually could just look at our regular force equation, where we're working with our mass times that centripetal acceleration. So we can actually just plug in our mass and substitute in this equation here for your acceleration. If you want to go ahead and do your speed in for this equation right here, you will get to the same answer. It's just going to require a couple extra steps. So we like to save time here. So let's be efficient, and let's just go ahead and jump to just our regular force equation. So your force is equal to your mass times that centripetal acceleration. So that's 4 pi squared r divided by your period squared. And then just to simplify this, I am going to move this mass into the fraction, and I'm just going to plug it in right here in between your pi squared and r, just so that way it matches what you have on your formula sheet. So that centripetal force is equal to 4 pi squared times your mass times your radius, all divided by period squared. So I'll just repeat that. So you could actually substitute the speed equation into this equation here that we had for centripetal force, but we'll get the same answer. Here we just did it a lot faster, okay? And also just to repeat, the usefulness of these equations is that if we don't know our speed, like say if we just knew maybe our mass, the radius, and the period, then we don't have to calculate our speed. So these equations, it took a little bit of work to find them, but they will help us in the long run, where we might have only one equation to work with in a question versus having to find your speed and then work with your force equation. I mean, if you did that, it really doesn't matter. It's just going to take you a little bit more time. So, it's up to you, but just be aware of that there are some really nice options here. So let's do an example. So the compressor blades in a jet engine have a diameter of 42.0 centimeters and turn at 15,960 revolutions per minute. So we're going to determine the magnitude of the centripetal acceleration at the tip of the compressor blade. And so as usual, I'm going to start off by just writing down what information I'm given. So this 42.0 centimeters is the diameter, which we know that for all of our equations we need to be working with radius. So let's go ahead and just convert that. So I'm going to take the 42.0 and just divide by 2. So our radius is 21.0 centimeters. The other thing, if you guys also remember from the other videos, is that we should be working with the same units. So this centimeters needs to be converted to meters. So we're going to divide by 100 to convert that to meters. So that'll give us 0.210 meters. So the next bit of information here that we're given is that the blade is turning at 15,960 revolutions per minute. So if you guys remember back to, I believe that might be our second lesson, where we had a discussion on something called frequency. So we are able to work with our frequency and convert it into a period, but once again we have to kind of go back to this discussion that we had right here, is we need to make sure that this is in usable units first. So our frequency here is 15,960 and it's revolutions per minute. So I might even write it like this, revolutions per minute. So in order to convert to, say, our period, we want to be working with revolutions per second, because then our units for period would just be seconds. So this revolutions here is fine, but we need to get rid of this minutes. So we're going to use our unit analysis to get rid of minutes and introduce seconds. So we want to get rid of the minutes unit, so we're going to put that on top. So there's 1 minute, and we're going to introduce the seconds, and there are 60 seconds in 1 minute. So then you're going to, here we have one value on the top, one value on the bottom, which means that we're going to divide those two values. So go 15,960 divided by 60. And when you plug that into your calculator, you should get 266, and that'll be revolutions per second. And these are the units that we want, because when we convert this to period, then we're going to be just working with seconds, and that's great. All right, and I guess just before we move on, I do need to make sure we account for sig figs here. So looking at this frequency here, we had 15,960. This value here has 4 sig figs, so our answer also needs to have 4 sig figs. So I'm just going to put in a 0.0 right there. And I'm also just going to scroll on down, just so I have a little bit more room to work here, because now we're going to go ahead and find that period. So if you guys remember from, I think it might have been the second lesson, we had the discussion about period versus frequency. So there was actually a relationship between period and frequency, that your period was equal to 1 divided by the frequency. So now let's go ahead and convert this. So we have 1 divided by, so it's 266.0. And if we plug that into our calculator, we should get 0.00375940. And I'm just going to go a couple values after my sig figs. So just remember, we had 4 sig figs here, so our answer is also going to have 4 sig figs, meaning this 9 is significant. All right, now I'm going to scroll back up, because now we can officially go ahead and finish this question. So here we're looking for the magnitude of the centripetal acceleration. So knowing here that we don't have anything to do with our speed, we can use the equation that we just came up with at the beginning of this video for centripetal acceleration. So that was equal to, so it's 4 pi squared r divided by your period squared. So we have our radius, we now have our period, which is great. So we're going to plug in our values. So we have 4 times pi squared times your radius, which was 0.210. That is divided by the period squared. So we have 0.00375940, and that value there is squared. It's going to mark off my sig figs. All right. So now we can go ahead and simplify. I think for a question like this, I mean, you either could put all of this into your calculator at once, or, I mean, if this one here might be a little bit recommended, just in case you make a calculator error, you might even want to just plug this into your calculator, do the numerator, and then just the denominator, and then throw the rest into your calculator afterwards. All right, so I'll do this step by step. So I'm gonna plug in my numerator into my calculator, and you guys should get 8.29047. And then just keep track of my sig figs here. I had 3 to begin with, so my answer will also have 3. And then to simplify my denominator, I'm going to put this value into my calculator and square it, which should give you 0.000014133. And then just to account for my sig figs here, I had 4, so my answer is also going to have 4 here. All right, and I am just running short in terms of time, so I am going to pick up the rest of this question in the next video, and that one should be the last video of our lesson.